We want to get a deeper definition of differential calculus, and essentially we're just looking for how a particular thing is changing. The way that we can interpret that is by considering the gradient of that point. We can see that as 2 points get closer, the more accurate the gradient is going to become. This lesson, I want to define the derivative. And so the easiest way to go about that is, let's just say I've got a random curve here, and I'm going to pick out a point. Let's say this is the point X, and that's going to have a corresponding y value of f of x. I'm going to pick a second point. You do it in green. Let's say this point here, and this is going to be the point, let's say x plus h. And when I say x plus h, I mean that there is some distance in between x and x plus h, which is just h. And that's going to have a corresponding y value of f of x plus h. Is putting whatever x plus h is into the function, it'll spit me out a y value, just for whatever this f of x is, that function is. I want to know what the gradient is at the orange point. Exactly. I don't want to know what the average gradient is. That's my goal. I want to know what is the gradient at the orange point, not the average gradient between the orange and the green point. So we can think of the gradient as y2 minus y1 over x2 minus x1. But again, I want to know what the gradient is at that orange point. And so the way that I can conceptualize this, if I zoom in here, at the orange point means that the green point is super close to the orange point. Or in other words, like, it's got to come right down. Like, this point has got to come right down all the way to, like, it's literally on top of it. It's as close as it's possibly going to be. Now, what that actually means is, if we consider the value for h, that means that this h point is going to get smaller and smaller and smaller. So the way that I'm setting it up is, I want h to be as close to 0 as possible. I'm going to write it out. What does that actually mean? If I want to determine the derivative, the exact rate of change at that particular point, I'm going to use some notation here and say that it's f prime of x. It's the derivative of f. And I'm going to say that that is the limit as h approaches 0, because I want h to get really, really, really close. That distance now I want it to get super, super, super small. And when we're calculating the derivative, it is essentially just a gradient. So it's just y2 minus y1 over x2 minus x1, which is f of x plus h minus f of x over x2, this guy here is x2, that's going to be x plus h minus x. And there's a little bit of cancelling there. Okay, so really what we've got for the derivative is we're saying that it is the limit as h approaches 0 of f of x plus h minus f of x, that's just y2 minus y1, over h. And this right here is the definition of a derivative. Or in other words, this is what we are going to use whenever I want to find the gradient at one particular point. If I wanted to find the gradient at that point there, that orange one, I would have to use my definition of a derivative, because the way that I've defined it is I'm saying that it is the gradient at that point. Because I've considered the 2 points, but h has just become 0. Let's have a look at an example. Calculate the derivative of f of x equals 2x squared minus 3x using first principles. The definition of a derivative is first principles. So I'm just going to start off by writing that down. So we've got our information out there, and pretty much in order to calculate the derivative using first principles, we need to know two pieces to our recipe. We need to know what's f of x, well that's this guy right here, and I also need to know what is f of x plus h. So I'm going to also write that out over to the side before I substitute it in, so I don't make any mistakes, because that is key. So f of x plus h, we're essentially writing out f of x again, but everywhere I see an x, I'm going to replace it with x plus h, because that's what the input is. So I'm going to say it's 2 outside of x plus h squared, not x squared, it's x plus h squared, minus 3 outside of x plus h instead of just minus 3x. I'm replacing the x with the x plus h. Now, what we have got here is I've got some information to throw into my definition of a derivative. And so there it is. We've thrown all the information into the definition of the derivative. Now we just have to simplify it out. So what we're really doing here when we're evaluating the limit is I want to substitute in h being equal to 0 and eventually find out what my answer is. However, we're dividing by h and we can't divide by 0. So we've got to do some manipulation here in order to get that out. So I'm just going to start off by just expanding brackets and see if things will cancel off. First things first, just as a reminder, I'm going to do this over to the side. Okay, so x plus h squared is x squared plus 2xh plus h squared. That's just the expansion of those brackets there. So I'm just going to write it out like that. And then here we'll minus 3x plus h, so it's going to be minus 3x minus 3h. And then here I'm expanding these brackets out, minus 2x squared plus 3x. All that is over h. I'm just going to keep simplifying this out here. Now, if you have done all of your initial substituting incorrectly and your simplifying of the stuff, you should have some cancelling happening. And actually all of the strictly x terms should just cancel off. So 2x squared minus 2x squared and minus 3x plus 3x. They all cancel off. So this simplifies things out nicely. It's going to be as a limit as h approaches 0 of 4xh plus 2h squared minus 3h all over h. And so again, all we're trying to do is we're just trying to calculate what the derivative is. So this is the process by using first principles. We're saying here as the limit as h approaches 0. So I want to eventually just substitute h being equal to 0, but I can't at the moment because I'm dividing by h. However, I can just factor out a h from this numerator because all three terms have a h. So I can say it's the limit as h approaches 0 of h outside of 4x plus 2h minus 3 over h, and those will cancel off. Then I'm left with the derivative being equal to the limit as h approaches 0 of 4x plus 2h minus 3. And as h is approaching 0, if you've got 2 times h, where h is getting closer and closer to 0, that's just going to be equal to 0. So when we evaluate this limit here, this is just going to equal 0, that term there. So we can then just say that the derivative function is equal to 4x minus 3. So you might be thinking, cool, what's the big deal? It's actually a pretty massive deal. All we did here, this is a rise over run calculation. So the derivative is going to tell me something about the gradient. It's going to tell me something about the gradient of this guy here, because that is how I've defined the derivative. Let's have a look and see how this works. And if we were to graph both of these functions on the same set of axes, we can see we've got the original function, f of x equals 2x squared minus 3x, and its derivative function, f prime of x, being equal to 4x minus 3. If we consider the point when x is equal to 1, we can see that the corresponding y value on the derivative function is 1. What this implies is that the gradient at the point x equals 1 on our original function is equal to 1. We can do this for any x point. Let's consider when x is equal to 0. The corresponding y value on the derivative function is y equals negative 3. If we consider the value of the gradient on the original function, we can see that it's got a gradient of negative 3. If we want to just put some words to what's going on here, we would say that evaluating any x point on f prime of x will provide the gradient at that x point on f of x. That is, f prime of x is equal to m, where m is the gradient on f of x. So here we've got calculate the derivative of f of x equals x squared plus 2x minus 1, hence determine the value of x that has a gradient of 0. Cool. So again, I'm going to need all of the pieces to the puzzle. All of my pieces. That is that guy here. This guy here is that guy there. And I'm going to make sure I substitute it in and evaluate my derivative correctly. Okay, and so just so I'm not buggering up any negatives here, I've got minus f of x, so I'm just going to put in brackets around the whole f of x term, which is everything in yellow. So I've got everything in here, and similar process, I'm just going to expand my brackets, see if things are going to cancel off, and see if I can evaluate my limit. Okay, just doing that first part there, expanding that x plus h squared, like we saw last time, it's just x squared plus 2x plus h over h. Then things should cancel out nicely. X squared minus x squared, 2x minus 2x minus 1 plus 1. That's nice. And then here, we need to evaluate the limit. So when h is equal to 0, we can't just put h equals 0 in at the moment because we can't divide by 0. H is on the denominator, so we need to see, can I get it out of the denominator? Same trick, h, and h is in common with all three terms, so I can factor the h out. And so this is what our derivative is going to be. Now we can evaluate the limit. You can evaluate the limit whenever you want, whenever it's illegal. We just can't do it before because we're dividing by h. You can't divide by 0. So we can do that here. This term here, that's just going to peter off to be 0. As h gets super close to 0, that term is just going to be 0. So we can say here that we've got the derivative f of x Now remember, the derivative is going to tell you everything about the gradient of the original function. So it says, hence determine the value of x that has a gradient of 0. Okay, if we can consider what we did last time, at any x point on the derivative function, the corresponding y value will give you the gradient for that x point on your original function. So let's just apply some logic here. I want to know when is the gradient, what x points does that occur? And so I can calculate that by saying, well, the corresponding y value of the derivative is equal to 2x plus 2. Or in other words, I'm letting the derivative equal 0. That's what I'm doing. And so I can rearrange and solve that and say that I've got 2x equals negative 2. So that occurs at x equals negative 1. Let's interpret this graphically. Here I've got my function. Here I've got my derivative. And so we can see that when in our original function is going to have a gradient of 0, that's when the gradient is flat along this line here. And that is going to occur exactly at this point here, which is x being equal to negative 1, which is very nice. And so that's our answer. And what also told us that is if you look at the derivative function, at that same x point, the corresponding y value was 0. That's this x point here had a corresponding y value of 0. Okay, that's that 0 there. And so you can interpret this, like you can just keep going with this if you like. You can say, okay, well, what about this point here? This point here. When x is equal to 0, this is the derivative function. When x is equal to 0, y is equal to 2. So that's going to tell me that at this point here, at that same x point, this has got a gradient of 2. This is just an idea that we're going to have to get used to. This is what differential calculus is, and we've established it by first principles.